Nobody expected an artificial intelligence to find what humans had missed for over 50 years. The Apollo program produced an archive of photographs so vast, so meticulously cataloged, and so exhaustively studied by scientists, historians, engineers, and conspiracy theorists alike that the universal assumption was that there was nothing left to find. Every frame had been examined, every shadow had been analyzed, every rock formation had been identified and categorized. The Apollo lunar photographic record was considered one of the most thoroughly scrutinized visual archives in human history. And then Grok, the artificial intelligence developed by XAI, was pointed at that archive and told to look. What it found in those images, patterns and anomalies that had been sitting in plain sight for more than half a century without a single human analyst catching them, did not just surprise the experts who reviewed the findings. It fundamentally changed the questions that scientists are now asking about what the Apollo astronauts actually documented on the surface of the moon. To understand why this discovery matters as much as it does, you first need to understand the scale of what the Apollo program actually captured on film. Between 1969 and 1972, 6 successful Apollo missions landed on the lunar surface. The astronauts who walked on the moon were equipped with Hasselblad cameras using specially designed magazines loaded with thin base film that could capture an extraordinary number of frames. They were not casual photographers. They were trained observers, executing systematic photographic surveys of the lunar environment with scientific precision. By the time the Apollo program concluded with Apollo 17 in December 1972, the astronauts had taken approximately 35,000 photographs, 35,000 individual frames of the lunar surface, the lunar sky, the equipment, the geology, the Earth hanging in the black distance, and the terrain stretching away in every direction from the landing sites across 6 different locations on the moon. NASA digitized this entire archive with high-resolution scanning technology and made it publicly available through the Apollo Lunar Surface Journal and the Johnson Space Center Image Library. The intention was scientific transparency, the kind of open access that allows researchers anywhere in the world to examine the primary evidence of one of humanity's greatest achievements. And for decades, researchers did exactly that. Geologists studied the rock formations. Physicists analyzed the lighting conditions to verify the physics of a vacuum environment. Engineers examined the equipment for signs of wear and performance. Historians documented the human story visible in the images. The archive was not neglected. It was intensively studied by thousands of qualified people over more than 50 years. And yet, Grok found things none of them had seen, because the way an artificial intelligence looks at an image is categorically different from the way a human looks at an image, and that difference turns out to matter enormously when the archive being examined is 35,000 frames of a completely alien environment where human intuition about what is normal and what is anomalous is deeply unreliable. Human visual processing is extraordinarily sophisticated in its own domain. We are superb at recognizing faces, reading emotional expressions, tracking moving objects, and navigating familiar environments. But we are also heavily filtered by expectation. We see what we are looking for. We notice what we have been trained to notice. And we are subject to a powerful cognitive tendency to normalize the unfamiliar, to fit novel visual information into existing categories, even when it does not belong there. When Apollo scientists examined the lunar photographs, they brought with them 50 years of accumulated geological and physical knowledge about what the moon was supposed to look like. That knowledge made them excellent analysts of the expected. It also made them systematically likely to overlook the unexpected. Grok approached the archive without expectation, without the filtering effect of prior knowledge about what should be there, without the normalizing tendency that causes human analysts to unconsciously categorize ambiguous visual data into the nearest familiar concept. The AI processed each frame as pure visual information, mapping relationships between features, identifying statistical patterns across the archive as a whole, and flagging any element that represented a significant departure from the baseline patterns established by the rest of the dataset. It was not looking for anything specific. It was looking for everything, simultaneously, without prejudice. The first category of findings that emerged from the analysis involved geometric patterns in the lunar regolith, the loose, fragmented material that covers the moon's surface to varying depths. The moon's surface is shaped by a well-understood set of processes. Meteorite impacts of varying sizes create craters with predictable morphologies. Ejecta from those impacts spreads in radial patterns determined by the physics of the impact event. Thermal cycling between the extreme heat of lunar day and the extreme cold of lunar night creates specific stress fracture patterns in surface rock. Gravitational settling over billions of years produces characteristic slope profiles and sediment distribution patterns. All of these processes have known signatures. Geologists studying the Apollo images had become expert at reading these signatures and understanding the surface they described. What Grok identified were regions within multiple Apollo landing site photographs where the surface texture deviated from all of these known process signatures simultaneously. not deviations explainable by one unusual impact. Unusual, not deviations that could be attributed to local geological variation. Systematic deviations covering defined areas where the statistical properties of the surface texture were measurably and consistently different from the surrounding terrain. Areas where the regolith showed organizational patterns that the known physical processes acting on the lunar surface do not produce. The locations of these anomalous texture regions were not random. When Grok mapped them across the archive, a spatial pattern emerged. The regions clustered around specific geological features, particularly around the edges of ancient lava plains called mare, around the rims of certain impact craters, and along what appeared to be subsurface linear features that had long been identified in orbital photography, but whose surface expression had not previously been mapped in detail. The clustering suggested that whatever was producing the anomalous surface texture was related to the underlying geology in a specific and consistent way, rather than being a random artifact of image processing or camera characteristics. Geologists who reviewed these initial findings offered several potential natural explanations. Differences in regolith grain size caused by sorting processes during impact, ejecta deposition could produce surface texture variations. Local variations in the concentration of certain mineral types that reflect light differently could create apparent texture differences in photographs. Subtle slope variations invisible to casual examination could alter the way sunlight falls across a surface and create apparent texture patterns in two-dimensional images. These are legitimate scientific considerations, and they were taken seriously. But when the specific anomalous regions were examined in detail against the photographic data from multiple angles and lighting conditions captured across different Apollo missions and orbital passes, the natural explanations became progressively harder to sustain for all of the identified regions. Some of the anomalous texture areas had been photographed from orbit by the mapping cameras carried on Apollo command modules, as well as from the surface by the astronauts themselves. The surface and orbital views of these regions showed consistent anomalies from completely different angles and lighting conditions, which rules out photographic artifacts related to camera angle or solar illumination as the explanation. Something about those specific regions of the lunar surface is genuinely different from the surrounding terrain. What that something is remains, as of the time this analysis became public, without a definitive scientific explanation. The second category of findings was more immediately striking and considerably more difficult to discuss in measured scientific terms without acknowledging the obvious question that it raises. Across the archive, Grok identified a set of features in approximately 230 individual frames that shared a specific morphological profile. Features that were too small to have been identified as craters under standard cataloging criteria, but that showed a consistent internal structure, unlike any natural formation type documented in the lunar geological literature. The features appeared as shallow depressions with interior surfaces that showed the anomalous texture pattern identified in the first phase of analysis, with boundaries that were more geometrically regular than impact crater rims of comparable size, and with a spatial distribution across the lunar surface that did not match the random distribution expected from the meteorite impact process that creates the vast majority of small-scale depressions on the moon. The size range of these features, their morphological consistency, and their spatial distribution pattern were the three elements that Grok flagged as statistically significant departures from null hypothesis predictions based on the known physics of lunar surface formation. Any one of these elements in isolation might be explainable through natural variation. All three simultaneously, consistently, across 230 separate features documented in photographs taken by different cameras at different sites over a 3-year period, represented a statistical signature that the AI's analysis indicated could not be attributed to chance at any reasonable confidence threshold. The expert response to this finding was precisely what the history of anomalous scientific discoveries would lead you to expect. Immediate and vigorous engagement with the methodology, searching for the flaw in the analysis that would make the anomaly disappear. Could the AI have been detecting photographic artifacts introduced during the digitization process? Could compression artifacts in the digital files have created apparent structural patterns in small-scale features? Could the training data used to build Grok's visual pattern recognition have introduced a systematic bias that caused it to flag certain types of natural formations as anomalous, because similar formations in its training data had been labeled differently? All of these are legitimate methodological questions, and all of them were investigated. The digitization artifact hypothesis was tested by comparing Grok's flagged features against the original film scans at maximum resolution, before any compression processing had been applied. The features persisted. The training data bias hypothesis was tested by running a parallel analysis using a different AI system with a different training history and comparing the outputs. The overlap in flagged features between the two independent systems was significant enough to rule out idiosyncratic training bias as the primary driver of the findings. The natural formation hypothesis was tested by geological experts who examined each flagged feature individually and assessed whether any known lunar geological process could account for its specific characteristics. For the majority of the flagged features, no single natural process provided a complete explanation. What remained, after all of these methodological checks, was a set of features on the lunar surface that the best available analysis could not fully account for through known natural processes, documented in photographs that have been publicly available for over 50 years, sitting unseen in the archive until an artificial intelligence looked at all 35,000 frames simultaneously and noticed the pattern hiding across them. The third and most contested category of findings involved something that Grok identified in a small number of frames, fewer than 20, that the AI flagged not for surface texture anomalies or morphological irregularities, but for what its visual analysis described as evidence of subsurface structural features, expressed at the surface through a specific pattern of thermal differential signatures captured in the photographic data. The Hasselblad cameras used by the Apollo astronauts shot in visible light, not in thermal infrared. They were not thermal cameras. They could not directly image temperature differences in the lunar surface. But temperature differences in the lunar surface produce visible effects that a sufficiently sensitive analysis can detect in ordinary visible light photography. The lunar surface heats and cools at rates that vary with material density, composition, and the presence of subsurface voids or structures that alter thermal conductivity. These variations produce subtle differences in surface albedo, the reflectivity of the surface material, that can in principle be detected in carefully calibrated visible light photography if the analysis is sensitive enough. Human analysts examining individual frames would not detect these subtle albedo variations. They are below the threshold of conscious human visual discrimination in the context of a complex lunar surface image. But an AI processing the entire archive with consistent calibration standards and looking for systematic patterns across thousands of frames is not limited by human visual discrimination thresholds. What Grok flagged in those specific frames was a pattern of subtle albedo variation that its analysis indicated was consistent with the surface expression of linear subsurface features of significant scale, features that, if the thermal differential interpretation is correct, would represent structures beneath the lunar surface extending across distances of hundreds of meters with a regularity of spacing and orientation that does not match the known distribution of lava tubes, fault structures, or any other natural subsurface geological feature type documented in the lunar literature. The implications of this finding are substantial enough that several of the researchers who reviewed the preliminary analysis requested that their names not be associated with any public discussion of it until independent verification had been completed. That is not the behavior of scientists who think they are looking at a digitization artifact or a camera lens flare. That is the behavior of scientists who understand exactly what the finding implies and are not prepared to attach their professional reputations to it until the evidence has been subjected to every available test. NASA's Lunar Reconnaissance Orbiter, which has been mapping the moon from orbit since 2009 with instruments far more sophisticated than anything available during the Apollo era, including a thermal camera capable of directly imaging surface temperature variations, has been generating data for 15 years that nobody had specifically examined in relation to the locations flagged by Grok's analysis of the Apollo photographs. The cross-referencing of Grok's flagged locations against the LRO thermal dataset is now being conducted. The results of that cross-referencing have not been publicly released at the time of this report, but the fact that it is being done at all, that the findings from an AI analysis of a 50-year-old photographic archive are being taken seriously enough to warrant examination against the best available modern remote sensing data, tells you something important about how the expert community has assessed what Grok found. The moon is not the dead, static, thoroughly understood world that the cultural memory of the Apollo program has allowed us to treat it as for half a century. It is a complex geological body with a 4.5 billion year history, much of which remains poorly understood. It has a subsurface architecture that orbital radar sounding has only begun to map. It has surface processes operating on timescales too slow for human observation, but detectable in carefully analyzed data. And it has an archive of 50-year-old photographs that, as it turns out, contained information that the humans who took them, studied them, and built their careers around them never fully extracted. The most important thing that Grok's analysis of the Apollo archive demonstrated is not any specific finding, however significant those findings may prove to be. It is the demonstration that the limit of human analysis is not the limit of what the data contains. We looked at 35,000 photographs for 50 years and believed we had seen everything worth seeing. We had not. We had seen everything that human perception. filtered through human expectation and human cognitive limitation, was capable of seeing. The data always contained more. It was waiting for a kind of attention we did not yet know how to pay. That lesson extends far beyond the moon. Every scientific archive ever assembled, every data set ever collected, every image ever taken, in service of understanding the natural world, contains information that human analysis has not fully extracted. The Apollo photographs were among the most studied images in history. If 50 years of intensive human examination left patterns visible enough for an AI to find them hiding in plain sight, the question that follows is not just what else is in those lunar photographs, it is what else is waiting in every archive we have ever built, in every data set we have ever collected, in every image we have ever taken of a universe we are still only beginning to learn how to see. The moon has been waiting 50 years for someone to look at it properly. It turns out we needed to build the right kind of eyes first.